All right, so hello everybody. Today I am going to talk about whether or what do these AI systems that we train have in their head, and in particular, what kind of world, or what kind of model of the world might they have in there. And so I want to start by stating something that might be obvious. Unless we're talking about embodied systems, for which we should, that would be next time, Dr. Fairley. The AI systems, the normal ones that we train with data, never actually see the world, right? They only get to see some artifacts that we humans captured and chose, gave to them, and yet we expect them to learn something about the world from these artifacts. And so it's kind of like looking at the outputs of a bunch of art students and trying to figure out what the subject matter is that they're all trying to draw, okay, just from these drawings. So if this is the real world, we may use a viewpoint from here and another from here and another from here and from here, and then we give all of these to some AI system, and then we wonder, what did you learn about the actual world? So it's kind of like, if you want to philosophize, it's kind of like similar to the prisoners in Plato's cave allegory, where the prisoners only get to see these artifacts that are chosen by humans and projected as shadows on the wall. And Plato's claim, of course, is that you're never going to learn anything about the world like this. You have to emerge and run away and that sort of stuff. Okay, so we don't know if they're learning about the world or about some data distribution. Give them, but we can still ask, what did they learn about the world? Okay, but we should think about something else. Okay, let's put upper bound for our expectations. Now we might argue about what this upper bound might be, and in fact, we do argue about these things. Some people think that AI models should be superhuman and they should have better models than human. I kind of think, you know what? The only thing we know that has a world model is us. And so we might as well look at what people can do, what kind of mental models we have, and use that at least to temper our expectations. Okay, so let's think about human mental models. And for that, we're going to look at Norman and his writing. And what he tells us is that humans have incomplete models. They are unstable, so we forget our mental models all the time. They're unscientific, so people are very superstitious about the world, and they kind of construct wrong models just to help them maintain their superstitious beliefs. They're parsimonious, so often people are willing to do a lot of extra legwork just to keep the model really simple in your head. We are really bad at running or simulating these models, and these models don't have clear boundaries. So a lot of the time, different systems get integrated in our brain into a single, so we get similar systems confused. Yes?
What does running a mental model mean?
Huh?
What does running a mental model mean? Like we're about other models?
Give me a minute. 2 minutes, okay? All right. So, all right, sorry, so we were here. Okay. But still, okay, so that would be an upper bound. We shouldn't expect too much of these models, even though sometimes we do. But even so, one central question we might ask is, how do we actually reach into someone else's head, whether it's a human or an AI, and try to read out what kind of mental model did they learn? So here's an idea. We might not be able to do that, but we can get a sense of what the world model is by looking at the affordances that it gives us. And for that, we're going to turn to Kenneth Craig. I thank Jitendra Malik, my postdoc advisor, for this beautiful slide. And we're going to read, okay? If the organism carries a small-scale model of external reality and of its own possible actions within its head, it should be able to try out various alternatives, conclude which is the best of them, react to future situations before they arise, utilize the knowledge of past events in dealing with the present and future, and in every way to react in a much fuller, safer, and more competent manner to the emergencies which face it. Okay? Yeah?
maybe it's based on instead, but why small scale?
This is what Kenneth Craig says. Because an organism might, in your head, might have something that's kind of small scale. It might not be a He's talking about biological creatures.
Okay, and second question is, this seems to ignore perception.
You mean like updating your...
Well, this seems to focus on reasoning, essentially saying, I know what the world is now, and the model is about predicting stuff, but in reality, we only observe them, understand what the world is like right now based on perception.
Yeah.
This
We
is-
also update our
this
model
seems
based on
independent of
perception,
perception.
right?
Hmm?
It's
It's
kind
independent of
of
perception.
independent. Like what he's talking about.
So this is by saying ignores it. It's orthogonal to perception.
Orthogonal to perception. Because this might get updated with perception, this might,
Okay.
Orthogonal. Good. If you squint for a second, if we squint, okay, then we might kind of distill what he's saying to basically the following. If you have a world model, you should be able to reason about possibilities, forecast the future, and generalize beyond your current experience, right? So Craig describes this small model in the head, but we can make this more precise and basically say, okay, a world model is not just knowledge, it's a way or a tool for simulation. So here's a minimal world model for you. You have a state, which is what the world is now. You have some dynamics, a rule of how the state might change. And once you have this, you can roll the world forward. You can kind of simulate what's going to happen in the future. So the current state goes in together with the current action, and the world model gives you what state will be in next, and you can rinse and repeat. And this is what we actually usually call forecasting, which is predicting future states, future motion, what's going to happen next. And in this framework, it's just repeatedly applying the dynamics. But this really isn't just about time. And kind of this is a key idea, is that reasoning and forecasting are not really different capabilities. There are two ways of using the same world model. So when we're doing forecasting, we're rolling out forward in time. When we are doing reasoning, we're changing the input action and we simulate our alternatives or counterfactuals. And so reasoning and forecasting are both types of simulations of Now in classical settings, we kind of write down the dynamics, but in modern AI, we usually learn this from data. But the structure is the same. You have a model that you can simulate. So this gives us a concrete way to test Craig's idea. We can't usually just read out what the systems know. Sometimes we can, most of the time we can't. But we can ask, can a system use its internal model to simulate the world? So what we know is that we know that if a system has a world model, it should be able to do reasoning, which is simulate possibilities, should be able to do forecasting, simulate the future, and it should generalize to new settings. So these are all observable affordances from the outside. I don't need to be in your head in order to ask you these types of things. And so it gives us a way to test aspects of world models by probing systems behavior. I'm just looking at Greg's questionable face.
So can you go back to this question? How do you observe someone's...
I ask you questions about basically the current state of the world and what are discussed.
Okay, so behavior here includes answering.
Yes, yes, I'm going to probe, yes.
So we want to think about this in terms of the dynamics. Forecasting, the state and action are fixed, and I just want to predict the future. Reasoning, the state is fixed, and I can change the action and predict. And then generalization is the state changes. Maybe the actions change or not. Is that...
Yeah, that's good. She makes a slide. Yeah. All right, so what we can do then is we can take these abstract ideas and capabilities and we can use them to measure behavior. So for example, reasoning, I can actually see, can you handle counterfactuals? And in this talk, we're going to have, I'm not going to test a complete system with a world model. We're going to look at different systems, and we're just going to look at different aspects of what sort of understanding of the world they have. And so for reasoning, we're going to look specifically at large-scale spatial cognition. For forecasting, we're going to look at motion forecasting, and also for generalization. So if you succeed on these tasks, what does that mean? It means that you've captured, your model captured some sort of structure, okay? It's not just patterns. But if you failed, it means that, okay, you're either missing or you have an incomplete world model in your head. So let's start with reasoning. If a system has a good world model, a spatial world model, it should be able to mentally simulate spatial configurations. And everything that I'm showing off today is like very much hot off the press, and so things are still in flux. So it would be nice to kind of hear your thoughts about all these different things. So here we're looking at visual language models. They're kind of nice to play with because they have visual and language grounding, and they're potentially capable to do this sort of implicit simulation. And we're going to look at spatial intelligence. When I say spatial intelligence, I could mean one of two things. One thing is small scale. So in a single room, I can see everything. The questions are more about object pose and object location. Or you can talk about large scale spatial representations, which are more, let's think about city scale. You don't really see the whole space from anywhere that you're standing, and you have to use locomotion and path integration in order to build a representation of the world. Okay, and we're going to be in the second type of set. So what do we do? In this project, we looked at city scale walking tours. So these are videos that people who are, I don't know why they do this, but some people do this. They take a camera and they walk around the city for, let's say, an hour. So this is an example from Amsterdam, right? So this is what you have, video, person, walking. And we have, you know, it's very real world, it's high resolution, it's very long. It could be an hour or longer that people film these things. And it's all filmed from a first-person view. And so what we do is we collect these videos, and now we think about, okay, if we give these to a model, what kind of things can we ask about in order to test spatial reasoning? And so for this, we kind of think about what people have done in cognitive science about mental maps. And what we know about people is that there's 3 levels of spatial understanding, really. We can think about landmarks, so that is kind of, can you recognize some specific place? Can you localize particular objects in space? Then from that, you build route knowledge. So that means, okay, I'm going to walk around the world. Can I think about how to get from point A to point B in my egocentric viewpoint? And the third level is to say, okay, I not only can go from place A to place B, but I can also integrate across all of these routes and build some sort of survey or map knowledge, which is kind of world-centric, and I can put all of these routes together. Okay? So we designed a benchmark that captures all of these levels of understanding. And here are some examples of questions that we asked. So here are some landmark level tasks. I can ask simply, can you recognize this building? Has it appeared in your video? I can ask, what is the distance to a landmark from where you're standing now? I can ask, have you seen a loop? Have you gone through a loop? So have you been to the same place twice in this video? And just to give you a visual, this is what a loop would look like. You start and end at the same place. This is when there's no loop. Of course, the models and the humans who are answering these questions don't have any access to the maps. They're only seeing the video. Another question I can ask about routes is, okay, you walked through the city. Now I can give you different text-based route summaries and ask you which one is the one that you've seen. And in terms of map knowledge, I could do things like, okay, you walk through the city, now I'm gonna give you 5 different options of maps, which is the one that matches your route. And I can do this with text on the map, or I can make it a little bit harder and give you no text, so you can't do, street sign to map matching. So we have a bunch of tasks like this. The setup is, again, model, humans only see the video, and we're gonna ask all these questions. The problem is that it's very hard to extract ground truth for these things. Like, how do I test and do it automatically? And so what we did is we used existing services to ground the videos on the map, okay? So if you have a video,
So you don't have GPS,
I
these are
don't have
just
GPS,
videos.
just video. It's like literally YouTube videos. And so we need to basically reverse engineer the GPS. And there's ways to do that. There's an open API called Google VPS. It's called the Visual Positioning Service. And we literally ran it frame by frame, not every frame, we did 1 FPS, but on the videos to align them with the maps, okay? And this is cool data because we're gonna release it. And so there's a lot of stuff I think we can do with this type of data. Yes,
Does this service treat the frames independently?
it does because it's not very smart. So there's definitely ways to make it better. But right now, the service is really for, the reason it's open is because it's for people who walk around with their phones and they're like, where am I? And then it gives you a
So you're running like a common filter
Yeah.
or something too.
Yeah, we did a little bit of smoothing. We did a little bit of, but the open service itself is, Okay, so given this data, we ask a bunch of questions on these videos, and this is a little bit of the distribution of the different questions. In general, we have a benchmark. We're going to release it with 1,000 questions on the video clips, and each one comes with a multiple 5-choice answer.
So
Yes.
maybe it's a stupid question. So
No
technically,
stupid questions.
Technically, what that VPS thing gives you is the red line on the map, right? Roughly speaking.
Yeah.
Black line on the map.
Yeah.
But you need to then convert, if you want, for example, to have a text of route, you need to extract like the set of turns. Is that something which is easily automated?
What turns? Oh,
You have a
the
text
route.
of route, for example. Yeah. So-
Yeah. No, it gives you actual, because it's okay. So it gives you the actual point.
So it
gives
snaps. It actually
It
snaps.
doesn't draw on the map. It gives you
Studio
the
Line.
location.
I see,
And now I
I
have
see.
Google Maps, and now you integrate, and then you know.
Okay, so the location saying
Yeah.
turn right to route such and such is that's automatically
Oh, it's
extracted.
automatic, Yeah. No, this is not at the scale that we can do this way. We verify. Okay, so when we ran this, we verify some of this with the annotators, and then we make sure that but we don't. None of this is.
Let's do that.
Oh, you want to check that it's matching. Okay. So in the benchmark, we don't use an hour-long videos because there isn't a current model that can take that long. So we cut it up into up to 10 minutes at a time. And the other thing we do is we downsample to 1 frame per second because again, for most models we downsample to 1 frame per second because most of them cannot take more than that. And here are examples of what happens when you walk for 10 minutes. Basically, a normal person would cover about 1 kilometer. So this is the scale that we are talking about.
Will you tell us?
You are okay.
Will
Yes.
Will you tell us how you feed this much video to?
We didn't do anything special. So we're
What
testing.
model are you using?
Yeah, I'll show you. We're testing like Gemini. We're testing GPT. We're testing all the state of the art. This is in 1 frame per second when needed. There's some, I actually don't have the graph, but for some models, we could do up to 600 frames, and so we did, but a lot of them just do what fits.
Oh, I see. You said 30 frames per second. I thought you were.
That's
10
the
minutes.
original, that's the original video, but because a lot of these can't take that as context, we're downsampling.
okay. No,
Yeah.
that's-
And we're not doing anything special. There's no magic. Right? Okay, so what happens when you ask these questions? What Greg expected from the beginning when he was going to lead the talk, humans do much better than models. Okay, that's what you would say. Except for one corner case, which is loop closure, where somehow, okay, the humans are green. Sorry, humans are green. Models are everything else. Somehow for loop closures, models do actually pretty well. And so the question is, like, how? Like, really? And so what we did is we tried to look at the accuracy.
Loop closure is hard.
Loop closure is hard, and it's hard for humans, okay?
That's what I mean. I'm saying it's hard for humans.
It's hard for human. It's a very hard for human task because it's very hard for humans to do this in this way, which is passive, because you don't get any information from your proprioception. So this is actually a hard task for humans. But the way that humans do this is that you do path integration together with visual recognition. And what's interesting about these models is that if we separate the accuracy to visual recognition versus anything spatial, so in this case, can I actually just look at a image and see, have I seen this before, versus can I say, where has this object been in space? We see that, okay, visual recognition is really high, but asking anything spatial doesn't really work.
So visual recognition is, have you seen this building, or
Yeah, have you seen this, versus can you place it? Like where, how long, how far, where, that sort of thing. And the same thing you can see in loop closure, where the visual recognition is pretty high. The moment you start asking for when have you been in this place before? It's shaky. But still, it's better than the green human. So how does this happen? And indeed, this visual recognition is a hit, because when you go and you look at the traces of these models, what happens is the following. Okay, this is the image at the end. Okay, this is what you need to find. So what the model is going to do is going to say, okay, I'm looking at this place. By the way, it identifies it wrong, but I'm looking at this place, okay? And now I'm going to look frame by frame examination. I'm going to see, have I seen this before? And it goes and it goes and it goes on, and it looks frame by frame for this landmark.
humans cannot do that. They can't go back.
Humans cannot do that because, you could, but it would be very.
It's like you don't allow them to go back and watch.
Oh, to go back and watch. I think they are allowed to go back, but I don't remember. That's a good question. Yeah.
So your assumption here is that this text somehow faithfully reflects the internal representation.
I don't know, but it is all that I have. But there is nothing in this text, in the self-reflection, that tells me that it does anything like path integration. It's just, it does what it's really good at, which is be a vision model and just do recognition. There's no reason for it. So what we think is that they excel at this loop closure just because they completely bypass any sort of idea of path integration or survey method. Okay, one other thing you can ask is, do they use map knowledge to identify route? So here you had a route, and now you have to pick one of these maps. Which one is the right one that you've seen? And what we see is that it works okay. If I give it the ground truth text, like you went straight, you took a right, and the straight whatever, you took a left, yeah, it does better, all right? If I take away the text for the map, there's no difference, it doesn't actually care. But now if I give it the ground truth route in text, it actually does worse. So what we think from here is that the only reason it gets better with the actual play-by-play directions is because it just did text matching on the street names and so forth on the map. And by the way, if you take away the video entirely, you didn't get to watch the video at all. You just get the map. It does much better. And if then you give it the text, it doesn't matter with or without text, it does much better without the video. Which means that, you know, these models really don't want to look at the video. If you can just get away without it, they would be much happier because there's more allocation of computation in order to be able to process all this information. So do they use map knowledge? Okay, not really. Then we said, okay, can these models read maps? What if I give you the map? Okay, can you use it to help yourself do something useful? And the answer is, I'm not going to go into the numbers, but the answer is no. If I give you the ground truth map, it's not going to help you at all, pretty much. So, do these models, yes?
Maybe a little bit strictly for the VLM part, I think we saw a lot of analysis, including this one, ignore the visual input that you provide to the model, while in the robotic science, in many VLM models, they ignore the language instruction, but only focus on image. Do you have any suggestion why different large models tend to attend on different inputs?
Yes. And which models are those that you're looking for?
Specific models.
Which, like, example, give me an example.
I mean, for many VLM models, they just see an image and act. They don't care about the language.
But this is like one of the big like VLMs or
VLA. VLM tend to read the text, pay more attention on text, while VLA tend to pay more attention on
VLA is vision
language action
model. And I don't know that much about how people train those models. What I know about these VLMs is that if you think about how big companies work, they all had language models first. And then they decided, oh, let's have some vision in here. And so it would be really expensive to redesign everything and retrain everything. So the way these things are constructed is that they take the vision stuff and they stick it on like a Band-Aid. And so everything that comes from the vision encoders gets translated to language. All the reasoning is happening in language. And so these models are not even as good. The vision models are not even as good as state-of-the-art standalone. And so that is why there's a lot of bias towards the text information here. Now, the vision language, the VLA models might have been trained more from scratch, in which case I would assume people did the right thing and really integrated it. I don't know, I would like to learn about it, but I haven't learned this. Yes.
Can you say, can you describe again the no video variant for experiment? What's the setup?
No video.
So you're just given, I mean, the model's not given the video,
No.
but given 5
It's,
routes and asked which one did I follow?
yes, but in this case, I'm also giving you the ground truth, play-by-play, turn-by-turn route in text.
Okay.
Okay?
Okay.
So you're allowed to use text, you
Yeah,
don't
okay,
have to use
okay.
Here you get the same text, but you also had to deal with this video that I made you watch.
Mm-hmm.
So you actually do worse. If I take away the video, you don't have to spend computation for that, and you can just do it. If you like, you just read books. Yeah?
Yep.
Okay. So, until now, we talked about reasoning by simulating different spatial arrangements. And that kind of went back to Craig's kind of try different alternatives idea. And now we're going to look at simulating future states by forecasting. And so here, what we want to do, completely different thing, no language at all, just video, okay? And what we want to do is we want to forecast future motion. Okay, so we have these videos of animals, and what we're going to do is we're going to extract point tracks. And these point tracks are dense tracks that are capturing, in this case, the ground truth motion. And the setup is that we have a model that observes a short 4-frame motion history. That was it, that was the motion history. And what we are asking it to do is to forecast what would happen in the future, okay? So this is that pattern matching, it's rolling forward some internal simulator of the learned motion. So we train this and we see that it works across a wide range of, in this case, animal species and behavior. And what I'm going to do is I'm just going to show you some examples because here the coolest thing is just the pixels. It's not perfect. That doesn't always capture legs. We have to work on our points on legs distribution. But overall, it is not bad. Surprisingly. Yes?
What if you do just nearest neighbor retrieval of this data set, since how well that works?
I'm wondering now if I usually have that, and I'm wondering if it actually have anything, but I don't think. But I will make sure now that we actually do.
Why did?
Yeah, but I'm pretty surprised.
Why do you not think it works?
Because I think we tried it, but now I don't want to say that because we just submitted it and I don't remember what we tried, but I will check.
I mean, it's also
I would be surprised if we didn't.
it's also a question of how large the set that you're looking
The
for
training
is.
set, but the training set here is pretty big. But the thing is that it's very long tail, so there's a lot of different animals, and we definitely separate, say, video snippets cannot be, both. Okay, so what do we do? We take a video. Here is an animal, we crop it. We look only within this crop. And then we collect a couple of things. So first of all, we have the point tracks on this animal, the ground truth point tracks, from which we take the points at the first time step. And we also pass through the dino. So I want to have some sort of visual appearance information. And then what we're going to do is we construct a token for each track. So each point has a track over time, and that is going to be the token for motion. And so we're going to take the dino appearance information, we're going to take the history of clean motion, those four frames of clean motion, and I'm not only taking the trajectory of the point, I also want to know, because it's 2D point tracking, some of these points are going to get occluded and going to appear again. I need to have an indicator of when they were occluded. Then I have, the future that is noisy, and all of this, and I have a positional encoding of where this point was in space. And what I'm going to do is I'm going to train a diffusion model to denoise these noisy futures. And we take a couple other things. One thing you need is the time step, and the other thing is an optional kind of guiding vector where I can say which direction I would like the motion to go, how strong the motion should be, and stuff like that. If you wanted to do some user-guided, motion synthesis. And so from all of this, we're going to predict the future trajectories. And so one thing you can ask, okay, you can look at pretty videos, but how do you actually evaluate this type of thing? The way you would normally evaluate things is that you would say, okay, I have some ground truth trajectory, I have predicted trajectory, let's just look at the distance, the L2 distance. The problem is that this assumes a single future, but future motion is multi-modal, so I should consider other options that didn't happen to be in my ground truth. And so instead of that, we want to think about the future as stochastic. So the thing we do is we fit a Gaussian to the ground truth motion, we fit a Gaussian to the predicted motion, and we basically look at the distance between those two. The way we do that is with distance between Gaussians, yes.
Why go? I mean, that sort of seems wrong.
Wrong
You
but
want a
simple, yes. Wrong but simple, yes. Yes. But what we do is the simple thing, which to say, okay, let's just look at the distance between Gaussians. It kind of looks at how far the centers are and how different the shapes are. Yeah.
But at this time, you don't have the clean motion. Because you're showing us just one.
This type.
Confused by
For
the
evaluation?
Clean history, yeah. Well, when you're running at the.
For test time, right now, I'm still dependent on it's not.
So the input is not actually the image,
it's
it's
not
a
an
four,
image.
it's a short video of
It's
4
a short
frames.
video of 4 frames. Yes. You could do it from image. You actually have the simulation from image, but I personally am under the opinion that that is more to me than looking at some history. And, but we can argue about that later. So if we look at these distribution statistics, we can actually come up with metrics that make more sense than L2. There's all kinds of metrics. But in terms of looking at the actual, what does it mean in practice, you can see how when you sample multiple seeds, you would often get motion that is not exactly the same. It's not very different, but it is different enough that it would require evaluating not a single future, but multiple ones. So these are examples of what happens when you sample futures that are resampled from the same model. Yes.
What does some point from those Some.
What?
Some
Some?
tree. It does this.
Sam.
Some.
The
How does Sam work on this?
Yeah.
Oh, we
Maybe
use
this
Sam. Sam is not a baseline because it doesn't do forecasting, but we actually use Sam to do the initial segmentation of the animal, and we take points only within the Sam segments.
But some tracks points.
But in terms of tracking is perception. So for every frame that you give me, I give you points. I call that perception. Here we're doing forecasting, so we only perceive 4 frames, but I want to forecast what happens in the future. Sam doesn't do that for you.
Sure, it can be affected, but it's not good.
I challenge you. Let's do it. Okay? Yes.
How does this compare to using a foundation model for video generation and then just applying a tracker to video?
I love your question. Wait a minute. Give me a second. Okay, we'll get to it.
I love your creation.
One thing we can do is we can use the optional displacement vector in order to, encourage the forecasting to just do whatever we want. And so we can ask, give me movement to the other side, give me more, give me less, that sort of thing. This is mostly for fun, less for science, but it's kind of cool. This is a nice one where you can say, okay, I want the head to turn the opposite direction, or I want it less, or I want it more. There are some existing baselines, mostly from robotics, that do this sort of thing. But none of them really think about including points, and at the end of the day, they don't work as well on real-world data that is outside of the robotics lab. One thing we are comparing to here is what if we knew what, I have some oracle, I just take an average over all the points and I say, okay, I feed that as the velocity that I expect to see from the model. It also doesn't work as well. but this is the robotics baseline. Now we get to Michael here. What happens if you just use state-of-the-art video generation model? Now, this was done as an internship at GDM. I cannot publish things with VO, so we're using Stable Diffusion, all right? But the problem with Stable Diffusion is that it is pretty good on things that are within, you know, the main part of the data. Once you get to the long tail, it sometimes does really fun things. Like here the elk is growing a tail head. Here the bison is going into the water. You know, if you stay within those corgi dogs, everything looks great. The moment you move a little bit further,
What data set was this?
it's called MammalNet. It's a publicly available data set of mammal motion. And we're gonna release the segmentation in the point tracks.
Is this Stable Diffusion trained on that mammal motion data set?
Yeah.
Or-
Good question. I don't know if we retrained it or we just used it at test time. No, I think we probably just used it at test time. So all good questions, like just have the pieces of it. Okay. One thing we did before we started all of this is that we had to disentangle the camera motion from the animal motion. So we do a bunch of data pre-processing for camera stabilization, otherwise everything moves a lot and you can't do anything. So this is just a visualization of what it would look like with and without this type of camera stabilization. Without it, you're kind of screwed because the cameras here are moving along. Okay? Now we get to generalization. We said it would be really nice if these models worked out of distribution. And so in this case, we see that the model generalizes zero shot to non-mammals and to humans. And I think this kind of makes sense, at least to me. Here's birds. Okay? We didn't train on birds, it was only mammals. And the reason it makes sense is because if you look at animal motion and mammal motion, and if you think about, you know, if you were someone who grew up in the savannah, you would have seen there's just enough richness in the low level of motion. You kind of see it in everything. Maybe not in the, you know, whole animal regime, but if you think about local motion, it's very varied. And so it makes sense.
I mean, that one's a little surprising.
Which one, the
The
butterfly?
butterfly.
It's okay. It kind of gets that. It doesn't, you know, but it's doing something, which I wouldn't have expected.
And to be clear, the model doesn't see, you know, the model that's doing the forecasting doesn't see an image, it just sees points.
It's these points and dino features that are
And that's right,
local
dino,
dino
okay.
features.
So, my understanding from earlier when you introduced it, we also tell it what behavior you're observing?
No.
Oh, it was just for our, but you were saying like lion grooming.
Yeah, no text, no text. Quick, no text.
You can give a text.
But I don't.
Yeah. No, but you do, right? You said you can modulate the output.
With a vector
Yeah.
of motion.
Yeah.
Not with text right now.
Oh,
No text.
oh.
So what we're hoping to do is we have behavior labels. They're not very good at this data. We're relabeling the data with behaviors. We want to use them for evaluation because what we want to do next is cluster this motion and do discovery and see if we can look at whether these motion trajectories kind of capture different types of behaviors, but no text is.
Start just trying to classify.
But my labels suck right now, so I need to get better labels for publication. Saying something really smart before, I don't remember what it was, but yeah. Okay, yes, so that I think that it makes sense because you see so many kind of low-level motions and their combinations. It makes a little bit of sense to me that it might generalize more broadly because it's a really nice kind of core set of data, even though it's not huge, it's not Google size, you know, it's an academic Okay, so you might ask yourself, fine, we did all this game, and it doesn't mean, what do we know? Do these models actually have world models? So let's just take stock of what we looked at. So yes, reasoning about, we just looked at large scale spatial tasks, kind of. Forecasting, we can do this pretty well in motion, but we've only looked at really short horizons. We're not yet looking at longer term, years. Generalization, okay, that really is the bottleneck in everything. Sometimes it works, sometimes it doesn't. We have 10 minutes. I'm wondering if we want to take a little bit of an aside. Yeah, let's do it. One thing you can ask, which is kind of a different tangent, is whether these models, there's only one world. If I train different models, at the end, if my data was big enough, doesn't matter which way I start from, are they all going to converge together to a single model? And there's been this hypothesis that this might be true. And so this is a very, still being in the press, it's not even out of the press, investigation of the evidence for this sort of thing. And so we took a look at this organic representation hypothesis paper, which claims that all these representations from different modalities are going to converge together, and we just looked a little bit at the experimental evidence. And what it turns out that the theory is very nice, but the actual assumptions computationally are very restrictive. So they assume that the world is small, that it is sparse, and that cross-modal mappings are all bijective. But actually the world is large, dense, and nothing is bijective. So things kind of break down. And so let me just give you a brief of how things are set up there. I have two modalities, modality A and modality B, and let's say that I have a single point in the world, and I can map it to modality maybe text and images, A and B, and this would be my query. In this image, I'm going to look at nearest neighbors. So I'm going to find nearest neighbors and maybe images and nearest neighbors in text. And now I'm going to see whether these neighbors match to the same actual thing in the world. And I can do this again and again. And sometimes those things match, and sometimes those nearest neighbors are actually not going to match to the same actual thing because distances are different in the two modalities. The way that people measure alignment between these modalities is with the idea of mutual k-nearest neighbors, which basically counts how many things are matching. So here are 2 green matches out of the 3 neighbors that we've looked at, so the score is 2, right? And in the evidence that was presented, everything is really nice because they're looking at a really small set of data, and the gallery is very sparse. So even if your neighbors are really far away, that's the best you can ask for. This is the closest thing you might have, and so you might match to things that are really far away. But what we show is the moment you look at real data that is larger, denser, those matches don't always hold. So actually, everything breaks down. And so when you densify, you look at a larger data set, all of this alignment breaks down, this doesn't hold anymore. And then also when you consider cases that are non-bijective, so for example, an image can be described by a bunch of different
images.
Rather way, yeah, they're just going to be described by the same text. Everything breaks down, and things are no longer objective. And so, in this investigation, we kind of say, okay, well, maybe the world is not really platonic. Maybe the guy who was right, who came up with the idea of Umwelt, where every animal, every organism really has their own view of the world, and they're kind of trapped in this soap bubble that goes around their head. They can't see anything outside of this bubble, and you kind of live in your own situation. Something to think about. So I don't know. World models may not always, may not all align to be the same thing. We might end up with a bunch of different models that are not all the same, different views of the same world. Okay, so what's missing, you know? What's missing in order for everything to work? There's a lot of stuff missing. Here's a couple of things. So one thing that's missing is this integration of reasoning and forecasting together. Another thing that might be missing is some sort of set of richer mid-level representation of which you can build these world models. We don't really, in most cases, have very explicit uncertainty declarations, definitions, measurements, hypotheses. We don't really have big models that really work in a multimodal way. And what I think we're really missing is embodiment that's situated systems that can experience the world in a more direct way. This hopefully will be this talk, okay. That's about it.
Time for questions. Sure.
Someone other than Greg. Yes.
A funny thought experiment that may not be realistic, but let's just assume in the world there are, in the first experiment, there are two shops at two different locations that they look exactly the same, you know, the same text, the same, you know, like shape. So a human would easily recognize, you know, I've walked a mile in between the shops. They cannot be the same shop. But I wonder if like a machine learning model gets gaslit, gets confused.
Yeah, that's exactly the problem. This idea that I can do this in a brute force way just by recognition is very efficient, but it's very brittle because the moment you have stuff like that, so you have things that are things like that, you get totally, you totally. Exactly. Yes.
A different kind of reasoning task for the first thing might be, okay, now that you've seen this video, is this a good place to go on a trip with my kids? Or what other questions should I ask? Like, this looks like it's summertime. Is this the kind of place that people jaywalk? What would happen if I walked into the fountain or send my kids in? Are there other people? I wonder if like things like that, you know, what do you think about that?
Yes.
Those sort of, you know.
So some of this is spatial, and some of this has more with semantic understanding. And so this is a project with folks at DeepMind who have worked previously a lot of these semantic questions more. And here we were trying to ask only the spatial cognition one. Because whether people jaywalk or not, or you know that sort of thing, I don't need to know where I am in the city. I just need to know what city it is, and I need to notice these things in the video. So, but I think these are all interesting, possibly more humanly interesting. You know, we can ask today about these. You know what I mean? Yeah. But yeah.
Since you were motivating the world models by what like human world models, whenever I see these kind of like forecasting works, I always like kind of wonder how this relates to human forecasting because we're obviously not doing like pixel level predictions of things. And I guess it seems like I haven't seen something that seems to capture the way that humans actually like make and use predictions, where it's more like coarse and something like, you know, things that would be surprising and I don't need to plan for versus things that are kind of in the realm of possibility and I should plan for.
There is some work. I'll point to later. People have started looking at that. It's a hard question. Okay, so two things. Here we're not doing pixels. So we're doing, we're actively trying to find what's a good mid-level representation that would not be pixels, because I don't want appearance and motion entangled together. But granted, it's probably much lower level than what we do. But I think that is a very good question, and it also has to do with forecasting, and it has to do also with compression, because at the end of the day, depending on my task, I might not care about a lot of the information, right? So if you're thinking about video compression, or if you're thinking about, state representation compression for systems, you only need to, if you know what your task is, you only need to represent that stuff. It might be in the pixel level, it might be in the object bounding box level, it might be in the semantic level, or it might be just where in the future do I have a decision? And I don't care about it. Which is kind of like if you think about when you walk home, you have no idea. If I asked you to draw your cognitive maps, you would have no idea what happened either way until you get to the point, some place that you know I need to turn left next to whatever, right? So you totally throw away all that information because you know are not trying to find, I don't know, some post-it note on a wall. You're trying to just get home, so you only need to identify your decision. Right, yes,
For the last part,
yes.
so you mentioned it's because the world is more dense or not bijective, but I wonder, is it possible that just a representation problem, you couldn't match the nearest neighbor? If there might exist some representation, you can still.
Sure, but then there may be another representation that's aligned, right? But the Platonic claim is that all the representations are going on. And in particular, here all the experiments are with text and images, right? So text representation and images, so like llama and dino. Yeah. There might be another representation that would align better with one of them. And there might be other representations of the data that do align. But the question is whether